Hi, so first of all, I would like to present about the background of the problem. So there are two materials used. So the first one is aluminum alloys for panels and brackets, and the next one is the carbon steel for shafts and gates. So basically, we use aluminum because it's lightweight and corrosion resistant, and we use carbon steel because it's high strength and wear resistant. So basically, we had a problem with both our materials. So the first one for aluminium, it's bending and loss of structural integrity, and the next one steel, we have serious fractures including cracking and chipping. So a new batch of conveyor fails during operation. So both materials fail. So we are here to investigate and determine the root cause. So the next one is the objectives of this presentation. So first of all, we will evaluate the microstructure of the imported steel. Then we will assess strength, hardness and ductility of both our materials, aluminum and steel parts. Then we will identify the root cause of material performance issues. Then after everything is done, we will recommend the most suitable testing and failure analysis methods. And last but not least, we will strengthen the critical thinking, teamwork and problem solving skills. Well, guys.
So we will continue with the research planning and experimental design. So for our working plan is we use several tests, which is the tensile test, hardness test and the metallography test. So for tensile test, the purpose is to quantify yield strength, ultimate tensile strength and ductility of both materials. We use the equipment, which is the Universal Testing Machine UTM with the S tensiometer. The expected output is the stress strain curve, quantifiable the yield strength and ultimate tensile strength for comparison with specification. So for the second test, the hardness test, is to measure the bulk and case surface resistance to deformation. The equipment, we use the Rockwell hardness tester and the expected output is the hardness values for both materials. For lastly, the test for metallography, we to inspect the case microstructure, cast depth and defects. Equipment that we use is the optical microscope, mounting press, polisher grinder and etching. Expected output is the micrograph showing microstructure. And the safety and laboratory procedure, PPE was required. Safety glasses, lab coat and glove. Careful handling of needle etchant to avoid chemical burns. Universal Testing Machine UTM operated with control setting. Safety steps taken to prevent sudden fractures and flying debris.
Next, I will be present about the experimental results phase 1. There are a few methods that we use, that is metallography, hardness test and also the tensile test. For the metallography, there are a few steps that we use. The first step is standard specimens prepared following ASTM E3. The second step is sectioning, steel piece cut using abrasive cutter with water cooling to avoid heat damage. The next step is mounting. Sample mounting in bakelite resin for protection and easier handling. The fourth step is grinding. Sequential grinding with SSC papers. We use the 240, 320, 800, 1200 and 2000 grit, which is rotating 90 degrees each step. The next step is polishing. Polish with alumina or silica suspension until mirror finish achieved. The last step is etching. Etched with 2% nickel for 5 to 10 seconds to reveal ferrite pearlite microstructure, then rinse and dry. The diagram below shows a few pictures after the magnification from the 240 until the etching process. The next method is the hardness test. There are a few properties that we measured, that is the yield strength, tensile strength and also the elongation. For the aluminium sample, the yield strength is 169.432, the tensile strength is 190.892 and the elongation is 5.5%. For the typical AL6061T6, the yield strength is 275 MPa, the tensile strength is 310 MPa and the elongation is 12%. For the carbon steel sample, the yield strength is 510.738, the tensile strength is 648.866 and the elongation is 8.5%. And lastly, the typical AISI 1045 normalized. The yield strength is 450 MPa. The tensile strength is 655 MPa. And lastly, the elongation is 16%. The last methods that we use is tensile test. We provide two graph for the aluminium and carbon steel, and we measure it by using the stress in MPa and the strain in percent.
Right now, I will present data analysis and interpretation, phase 2, focusing on both microstructure analysis and mechanical property analysis for the carbide steel component and aluminium bracket. First, microstructure analysis. Let's look at the carbide steel here. From the microstructure, we can see martensitic light in the case and ferrite or pearlite in the core. However, there were critical defects such as quench crack and localized brittle carbide networks. This defect occurred because the carburizing or quenching process was not done properly. Uneven or overly fast cooling generated high internal stresses, which eventually caused crack and resulted in brittle failure. Next, for the aluminium bracket, the microstructure show large aqueous grains with absence of fine precipitate. This indicates that the bracket skipped the T6 aging process, leaving the material in a soft anneal condition. This explains why the aluminium had very low strength and failed easily. Now, moving to the mechanical properties. Aluminium bracket. The aluminium bracket record a yield strength of only 169.4 megapascal, which is below the required, which is 240 megapascal. Its hardness is 18 HRB, meaning it is fully anneal and very soft. Due to the incorrect or skip heat treatment, the bracket developed a large grain microstructure and therefore cannot resist load, causing it to bend easily. Carbide steel component. For the steel component, the core strength is 510.7 megapascal, which is acceptable. However, chipping and cracking were observed on the surface. The case hardness is 56.1 HRC, still below the standard of 58 HRC. This showed that the heat treatment was insufficient, resulting in a soft surface layer. As a result, the component experienced premature wear and surface failure. The brittle chipping further confirmed defective or improperly treated steel.
Assalamualaikum. Today I will be presenting a root cause analysis of some material issues and I will propose solutions to address them. Let's start with aluminium. We found that the issue stems from the wrong heat treatment, causing the material to become too soft with no strengthening. The immediate action we took was to reject the whole batch as it was too weak. Moving on to carbureted steel, the problem lies in poor carburizing and quenching, resulting in a soft surface and defects that cause brittle fractures. As a solution, we decided to reject the whole batch for the same reason, as it's too soft and likely to fail. In our root cause analysis, we have identified the core problems, which is wrong heat treatment for aluminium and poor carburizing for steel. These issues lead to material weakness that compromise their integrity. And lastly, for proper solutions, we recommended two key actions, which is mandatory certification for each batch and ensuring quality control through certificates of conformance, and process auditing, focusing on refining the supplier's heat treatment process to prevent defects. Now for conclusion, this analysis confirms that their failure were caused by major material issues due to poor supplier QC. The steel was too brittle and the aluminium was too soft. Our tests clearly identified the problems, giving us the evidence to replace the faulty parts and enforce stricter quality checks to ensure reliable, safe components for ABC Engineering and our clients.